Hello students, welcome back. Lesson 3A is gonna be relatively less important compared with other topics. We're gonna study 3 typical types of substitution techniques used for first-order differential equations, but those are relatively typical, not really typical. And all these examples here are, what can I say, relatively exceptional. That said, let's go. First type, homogeneous equations. What do you mean by homogeneous equation? A first-order differential equation in this type. A function of y over t. Why is it called homogeneous? Let's suppose we multiply y by c and t also by a factor of c. What happens here? Multiply by c, multiply by c. Hey, no difference. They cancel each other out. And in that sense, it is called homogeneous. Maybe you can see things better if I show you some concrete examples. Here's an example of a homogeneous equation. We have this factor here, this fraction here, and then we have 4 terms, ty, and another t and another y. They all have degree 1, homogeneous, same degree. How about the next example? We have 4 terms again, x squared, y squared, x squared, xy. They all have degree 2. Same degree, homogeneous. That's what it means. In that case, it is possible to simplify all those in this kind of form, y over t kind of form. And then what we are going to do is this kind of substitution. Take this y over t into another character, say v, and then we're going to go ahead with appropriate substitution. This will be v, and then what we need y prime, so we'll have to take the derivative. But if you take the derivative here, you have quotient rule, and how do you solve for y prime? That's really messy. Better to solve for y first easily, flip it over, and then take the derivative using the product rule. You see, y prime is derivative of the first function times the second function plus first function times the derivative of the second function. It's a product rule. Once you do that, that goes over here. And then what do you get? You get an equation of v. So this y prime here, that will be replaced by v plus tv prime. And this y over t here will be replaced by v. So you're going to get an equation of v alone. Now solve that. Once you're done, then you can go back to this one and then solve for y. Now if you go back and put everything in, the resulting equation will become separable. Let me show you. Go back here. That's y prime, and then y over t. Y over t is v, so that's becoming v. And then y prime is v plus tv prime, as we saw before. And then look at this equation here. That's separable equation. Flip v's to the other side, we get that. tv prime equals to f of v minus v. Does it look like separable? Not yet? Then what if I change this v prime into dv dt? What if I change this v prime into dv over dt? Does it look better? Well, t and this dt, multiply and then flip it over to the other side. Did I say multiply? Excuse me. Divide those out. And then everything here is expression of v, so divide everything away. All goes down to the denominator, so we have a separation. Again, this v prime, this is v prime, but it looks better with dv over dt. And then this dt flip over to the other side. And what do we have? We have this separation here. And then take the antiderivatives, calculate the integrals, and what do we have? We have an implicit solution. From here, you can either solve for v and then plug it into y, and then get the explicit solution, or sometimes you may have to settle with just implicit solutions. Either way, you'll have to use some separation of variables at some point. Alright, that was the theory, but theory part had too many symbols, so it was a bit difficult to handle. So let's go to concrete examples. This one is homogeneous, as you can see. First degree, first degree, first degree, first degree. They're all the same degree, so it's homogeneous. And then what do? Oops. Y prime is equal to, let's see, t plus y over t minus y. All right? But where are we headed? We are headed to this standard form, f of y over t. We need y over t. How do you get y over t here? Divide each term by t. Divide by t, that becomes 1. And then this one, divide by t. Divide by p, so it's 1. And this one, divide by t. That's what we get. And then, how do we substitute? V is y over t, this one. This one. I just highlighted it in red. So we will go here and then there. Now how about y prime? Let's find it. Y is equal to v times t. So y prime is equal to, by product rule, derivative of the first function times the second function plus first function times the derivative of the second function, but that's times 1, so I don't have to write times 1. There you go. And let me highlight this part in blue so that I can put it in right here. Make sense? Okay, let's do it. V prime t plus v is equal to 1 plus v over 1 minus v. After substitution here, this is what we get. Does everybody agree? Okay, all right. Only this one has t in it, so the other part flipped away. V prime t is equal to 1 plus v over 1 minus v. Minus v. Some simplification is in order, so let's take the common denominator. 1 plus v, okay, that's all set. And how do you take care of this subtraction by v? V times the denominator. So that's equal to, let's look at the numerator, 1 plus v, which was there before, and let's break out the second parenthesis, minus v, and then plus v squared. Do you see cancellation? These two cancel out, and what do you get? 1 plus v squared over 1 minus v. Okay, we are ready. V prime t is equal to that, and it looks better if you rewrite this v prime t into dv dt. It looks better this way. Okay, let's take the separation of variables. Divide this one away to the other side so we get the reciprocal function. 1 minus v over 1 plus v squared. And then flip this t and dt to the other side, so 1 over t dt. The separation is complete, and let's take the antiderivatives. Okay, left-hand side is going to be a bit of a problem. As you can see, it's complicated, but the right-hand side, that looks pretty simple. Antiderivative of 1 over t, what is it? It's log function, isn't it? So that looks good, but this one needs some work. Any idea how to do this? Any suggestion here? Maybe you may want to stop this playback and work out this integral on your own. Any idea? Well, please note that 1 over 1 plus v squared, that's one known function, and then removing this one, v over 1 plus v squared, that too is benign function because numerator is basically the derivative of the denominator except for constants. What am I talking about? Let's separate this integral into two pieces. This minus that. Now, what is this integrand? What's the first integral? It's arctangent. So this will give me arctangent of v. Now, how about the second integral here? Derivative of denominator is 2v, so we need 2v, all right. Balance out. And then what we have, derivative of denominator is the numerator right here, so we are ready. 1/2 log of 1 plus v squared. Oops. I guess I clicked some wrong key. And that's equal to log of t plus some constant c. Let's see. I feel totally comfortable with the log of 1 plus v squared because that's always positive. This one, I cannot say the same because log of t is not always valid. You may have to consider log of t, also log of negative t as well. So there's a bit of work to do. It's not an insurmountable work, but some work to do. About arctangent, I think it's all set. I don't think we can do anything any further here. All right. Okay, v is y over t. So let's put those back in. So this one is y over t. And then this one over here is y over t. And then we have this. Well, we have a, what do you call, implicit solution here, even though it's not really perfect. Number one, it could be simplified a little bit further. I don't think it is possible to solve for y explicitly, but it could be simplified. And then another thing is this log of t here. Inside has to be positive, so you may have to consider log of positive t or negative t. But in any case, I guess this problem is okay as is. But then again, we have a little bit of time left here and then not enough time to start a new problem. So let's continue working this thing, you see. This may not be really required thing, but let's do this anyway. Okay, let's start from here. Let's try to simplify this thing. How can we do that? Let's see. Let's get these logarithms in one side. Arctangent of y over t is equal to 1/2 log of 1 plus y over t squared plus log of t plus c. Let's put some space in between. Okay, that's okay, all right. That's all right, we can deal with this. And then let's simplify this thing a little bit further. Let's remove this 1/2. Multiply by 2. Multiply by 2. Multiply by 2. Multiply by 2. But then again, 2c. And let's take another character. Okay. Looking good. And let's take one more step here. Another typical technique whenever logs are concerned. We have this 2 log. How can you simplify it? Let's use the log rule to move it up here. And I feel a lot better now. Why? Inside of the logarithm is now always positive. I don't have to worry about positive, negative, different cases. We still have what do you call the singularity at t equal to 0, of course. We have something down here. But otherwise, this thing is looking good. One more step. Just one more step, and then we're going to be done. Log plus log. So we can use a log rule to multiply those things inside. So multiply by t squared. Multiply by t squared. And this is further simplification. This t squared and this t squared downstairs cancel each other out. You see t squared here and t squared there, and you get y squared. And that, I will say, the final form. So this is actually okay. It's an implicit solution, not perfect because we have some domain issue here, but well, I'll say this is a solution. And then this one is some further manipulation or simplification. Okay, all right. Okay, we're using computer algebra systems, so why don't we take one more step and do some verification as well? Let's clear some variable. It's always a good idea to clear all those variables before starting anything. And then I don't have explicit definition of y, so let's use this one right away. So 2 tangent, arctangent of y over t equals, we need double equality. If you have just one equality, then mathematical will understand it as naming or substitution. So this is the equation we have, and we're doing differential equations, so let's take the derivative. Let's take the derivative d, bracket open, and I'm taking the derivative with respect to my independent variable t. This is what we get. Too complicated, but I want y prime equals something something. So from here, I would like to solve for y prime. So solve percent. Percent means previous output with respect to y prime of t. And I have, oh, I made a mistake here. Y is wrong, y of t. Y of t is a function. Y will be considered as different variable. Anyway, we have what we want, right? Multiply by -1 to both numerator and denominator. We have t plus y, and if we have t minus y, that's precisely what we have here.